Okay. Thank you very much for the invitation to this conference, which had a difficult life, but I'm very happy that at the end you managed to organize it. So thank you also for inviting me here. And I also have to thank Thomas, who introduced this finite temperature integro-differential Painlevé equation, because I will speak about that. And so he gave a great introduction on that. Okay, so here's the plan. Sorry. Edition, presentation. Okay, here's the plan of the seminar. So I will introduce this generalization of the Tracy-Widom distribution, which originally appeared in the Kaldaq-Parisi-Zank equation. So it's the same kind of distribution that Thomas was speaking about, but in this case, this weight that for him was the cumulative distribution function of Gaussians. For us, it will be the Fermi factor or logistic function. And then I will describe that there are sort of three different Riemann-Hilbert approaches on the study of this type of distribution function. One is due to Thomas Botner, and I will not speak about that. And then there is a classical Riemann-Hilbert problem that you can study, which is something that I studied with Tom Claeys and Giulio Ruzza. And this will be the first part of the talk. And there will also be a small detour on some work in progress that I'm doing with Giulio Ruzza about a discrete version of this stuff, in which instead of having a finite temperature Ivy kernel, we have a finite temperature discrete Bessel kernel. And then there will be a second part of the talk in which I will show how you can use also operator valued Riemann-Hilbert problems to study these kinds of distribution. And as I said before, these are joint works with Tom Claeys, Giulio Ruzza, Thomas Botner, and Sofia Tarico. So the idea, as we said before, is that we want to study a deformation of the Ivy kernel. So I recall that usually when you define the classical Ivy kernel, you take an integral from 0 to infinity of a couple of Ivy functions. Here, instead of taking the integral from 0 to infinity, we take the integral on the whole real line, and we weight it with this function that I call sigma. So this Fermi factor, okay? This function that is here. And then what we want to study is a distribution function on the variable s that depends parametrically on t. And this is defined as this Fredholm determinant. The Fredholm determinant of the identity minus the operator defined by this kernel here, which depends on this variable big T, restricted to the interval minus s to infinity. Okay. And here, well, this is just the classical definition of the Fredholm determinants. And this is distribution function that already appeared in the literature. There is an article in 2007 by Johansson in which he relates this to these MNS matrix models and also a sort of deformed GUI. And then, and probably this is the, up to now, I would say that this is the most important application. This distribution appeared in the study of the narrow wedge solution of the Kaldaq-Parisi-Zank equation. And more recently, and I will speak a little bit about it in the second part of the talk, this kind of distribution appears also in the study of fermionic cistern at finite temperature. And also there is a discrete version of this story, which appears in the study of Schur processes, periodic Schur processes. So some discrete point processes that are associated to probability measures on the space of partitions, integer partition. So as we said before, as Thomas said before, this QST in a way interpolates between the Gumbel distribution and the Tracy-Widom distribution. And this is something that already appeared in the paper of Johansson in 2005. So here is just a recall that if you take x1, xn, some IID random variables, normal random variables, and you ask yourself how the maximum of this independent random variable behaves, up to some rescaling that are written explicitly here, you have that the maximum of this collection of variables converges in low to the Gumbel distribution. And this is the cumulative distribution function of the Gumbel distribution. And this QST, indeed, is something that gives a crossover between the Tracy-Widom class, universality class, and Gumbel distribution, in the sense that you have that the limit for t going to infinity of q minus st converges to the GUE Tracy-Widom distribution, while doing some rescaling and sending t to 0, you arrive to the Gumbel distribution. This limit in particular is easy to guess, at least from a heuristic point of view, because if you look here at the definition of this kernel, you have this sigma multiplied by t 1/3 r, and sigma is defined here. If you send t to infinity, this sigma becomes the indicator function of the positive real lines, and so you recover the classical IV curve. And this is how you see that in the limit for t going to infinity, you get the Tracy-Widom distribution. And I will not speak about KPZ, but in this paper in which they studied narrow wedge solution of the Kavdak-Parisi-Zhang equation, Amir, Corvin, and Castel, they had this very interesting Tracy-Widom type formula that relates this Q to an integro-differential version of Painlevé 2. The formula is this one, in which it is stated that this function Q can be expressed as a double integral, in which once you have a function u of two variables, x and r, once you integrate against sigma prime this function u square with respect to r, and then you do one more integration here, and you obtain your function q. And what is this this function u? Well, this function is a function that satisfies an integro-differential version of Painlevé 2, which is this equation, which is here. And of course, as it has been observed before, we said that this sigma tends to the Heath side function. So at least formally, when you take the derivative, well, you have the Dirac delta function. And this equation here reduces to the Painlevé 2 equation. And this formula is the classical Tracy-Widom formula, giving their distribution in function of Painlevé 2 transcendence. And of course, we also have to have boundary condition to fix uniquely this function u. So we have this nice connection between a certain Fredholm determinant and Painlevé transcendence, and it is just natural to ask how you can explain this connection. And there is a classical theory that you can use to explain this connection, which is this theory of integrable kernels, which is due to Isizagin, Kolepin, and Slavnov, which essentially, I'm not giving you many details on the theory, but essentially it tells you that whenever you have a certain integral operator with a kernel of this form here, in which f and h are vectors, then you have that the resolvent of this operator can be computed, or at least described, solving a certain Riemann-Hilbert problems on the contour sigma on which your operator is defined, with a certain jump matrix, which is explicitly described in function of this function f and h that you used to construct your integrable. Okay, So what we want to do is to use this theory to explain how this connection between Painlevé transcendence, integro-differential Painlevé transcendence, and Fredholm determinants appeared in this paper by Amir, Kovin, and Castel. And the idea, indeed, is that by a quite simple computation, well, we added this kernel we define in this way, but can be rewritten, it's very easy to do that, as it can be written in this form. And if you look at this form, this is more or less the form that we have here, except for the fact that here you have a sum, and this is okay, because these are the sum of the components of the two vectors f and h. But then we also have an integration on R against this sigma prime, okay? So this suggests that in a certain sense, and that I will make it precise afterward, in a certain sense, this kernel can be thought as an infinite dimensional IIKS integrable kernel, okay? And indeed, this is not completely surprising, because if you think about this, if you look at this paper by Amir, Kovin, and Castel, you see that indeed they use a generalization of the Tracy-Widom procedure to obtain this integral-differential Painlevé equation, and this was in 2010. And then in 2020, Thomas Barton found the first operator-valued Lax pair for this equation, okay, using an operator-valued Riemann-Hilbert problems defined on the interval 0 infinity. Okay, this will appear in the second part of the talk. But before speaking about that, I will speak about an approach which is somehow simpler to the study of this Fredholm determinant. And this is a joint collaboration that I had with Tom Claeys and Julia Woods. And this collaboration is based on a very interesting result, which is present in already in the paper of Amir, Kovin, and Castel in 2010, but then it was made more explicit in a paper of 2016, which says that this QST, which was defined as the determinant of a certain complicated kernel restricted to the interval minus s to infinity, actually can be computed as another Fredholm determinant with a kernel which is simpler, okay? With a kernel which is here denoted with k, ai, sigma, s, and t. And it's written here. It's just that you take the classical IV kernel and you multiply on the left, on the right, by the square root of this logistic function, sigma, which you translate by s, and you multiply by t factor 1/4, okay? So here, you integrate on the real line, but still you have the dependence on two variables, s and t, and the dependence on the two variables, at least in the kernel, is very simple. It's simply due to this argument of the Fermi factor, okay? You have translation by s, and then a dilatation by t 1/4, okay? This is something that you can prove simply doing some algebraic manipulation that then has to be analytically verified, but it's just, I would say, manipulation of integral kernel. But it's also an equality which is interesting, because it says that your function QST that you're interested in actually is a multiplicative statistic for the Ivy point process. So when you have the Ivy point process, you have a random configuration of points on the real line. These points here, I denoted them with zeta 1, zeta 2, and so on and so forth. And then you compute the product from j from 1 to infinity of this 1 minus sigma computed at these points, okay? This is a random variable. You take the expectation with respect to the Ivy point process, and you obtain the function QST that you're interested in. So really what we are computing are multiplicative statistics of the very well-known Ivy point process, which is the point process describing the eigenvalues of GUI near the edge. But for us, from the point of view of integral kernels, this is also interesting because this KAI sigma ST, this is now an integral kernel of dimension 2 by 2, because it can be written as F transpose lambda times h of mu divided by lambda minus mu, where F and h are written here. Okay, if you didn't have the sigma here, this would be exactly the classical approach to the Ivy kernel. But here we have this deformation by sigma, which doesn't hurt so much. You will see that you get something which is very similar to the classical theorem. And indeed, using this representation of KAI sigma ST, you can write a Riemann-Hilbert problem on the whole real line of size 2 by 2 with jumps given by these metrics here. The identity minus 2 pi I F H transpose. Okay. And then what you obtain is a certain Riemann-Hilbert problem in which the jumps are somehow complicated because they depend on these Ivy kernels and they depend on sigma. Okay. But then there is a standard procedure, which is called dressing, to simplify this Riemann-Hilbert problem. And you use this standard procedure, and then you land to a different Riemann-Hilbert problems, which is easier to study. And this is the description of the Riemann-Hilbert problem that you end up with. For some reasons that will be very clear just in a moment, instead of using the variable s and t, I use new variables x, which will be equal to st power minus 1/6, and small t, which is just essentially the inverse of t plus a square root. Okay, and you end up with this nice Riemann-Hilbert problem in which now you have a jump on the real line, which is quite simple. It's just given by a triangular matrix in which on the upper right corner, you have this function 1 minus sigma z, okay? The Ivy function disappear, okay? But if you notice, also this translation of the function sigma, which is a Fermi factor, by s and t disappeared, but we pay the price to make it disappear from here. And the price is that now you have that the asymptotic of the function psi at infinity is somehow complicated in the sense that at infinity you have, well, some factors that are not so bad. You have this z multiplied by a Pauli factor divided by 4, a certain constant matrix A, and then the exponential of minus t for t times z power 3/2 plus xz power 1/2 multiplied by the Pauli matrices 1 minus 1. Okay, and what is the relation between this Riemann-Hilbert problem and the Fredholm determinant that we wanted to study? Well, the log derivative of the Fredholm determinant that we want to study can be written as a certain integral of the solution of the Riemann-Hilbert problem on the real line. Again, computed against the measure induced by the Fermi factor. Okay, we have this formula. And what is nice here is that if you're a little bit familiar with inverse scattering theory for KdV, you see that here you have something which is very similar. And in a way, more or less, you might say that this function 1 minus sigma plays a little bit the role of reflection coefficient for KdV. And indeed, we have this theorem proved with Tom Clays and Julia Ruzza, which says the following. And this comes really from the Riemann-Hilbert problem that I showed you before. If you define a function v as double log derivative of your function q, then now I think as a variable of the as a function of the variables x and t, and you add x over 2t, you have that this v solves the KdV equation. Okay, and moreover, we have a little bit more information because we also have that this function v can be written itself as this integral here that depends on an additional variable phi, which is just a solution of the Schrodinger equation here with the potential v. Okay, so here we are really fully in the theory, in the realm of KdV theory. So we have our Lax operator for KdV, which is given by this Schrodinger equation. And then we have a certain eigenvalue, which is phi. And we have this relation between phi and the potential v. And also, in order to fix phi, we have a certain asymptotic behavior of phi. So at the beginning, when we found this solution, these equations, we were a little bit puzzled because we were looking for this integro-differential Painlevé 2, but then actually we found this KdV. So that was very good. We were very happy, but then we were saying, well, where this integro-differential Painlevé 2 equation is hidden, and actually you see it's somehow it's hidden in these two equations, because as I explained here, you have this Schrodinger equation here, and then you have a certain relation between the potential and the wave function phi. And of course, if you plug the second equation into the first one, you immediately get this equation, which is an integro-differential equation for phi. And if you restore the previous coordinates, so if instead of writing this in function of x and small t, you write this in function of small x and small t, you recover this Tracy-Widom formula of Amir-Kovin and Castelli. Okay, and this equation plays the role of this integro-differential Painlevé 2 equation. And actually, as Dave noticed in a seminar, during a seminar given by Giulio Ruzza, actually, this formula that we have here, this is very, very similar to a formula that already appeared in a paper by Dave and Trubowitz in 1979, which is essentially the analog, but just for a certain function v that goes to 0 at minus m plus infinity, which is not the case for our function. Okay, so using this Riemann-Hibel problem, we discovered in a way that behind this Fredholm determinant of this deformed Ivy kernel, we have much more than just this integro-differential Painlevé 2 equation, which is already very interesting by itself, but you actually have solutions of KdV. And and the nice thing is that these results extend to the case of more general weight sigma, possibly also with discontinuities. And so what you get also from the point of view of the theory of KdV is quite interesting, because you, in this way, you produce a whole family of unbounded solution of KdV. And also you have explicit Riemann-Hibel problems. There is something on the discussion. Okay, and also what is interesting is that we have an explicit Riemann-Hibel problem describing this solution of KdV, and this means that you can do nonlinear sleep resistant on this Riemann-Hibel problem, and you can study the behavior of this solution uxt around t equal to 0. So if you go back to this expression, you might guess that v is singular at t equal to 0, which is the case, but actually you have a very interesting behavior around t equal to 0, which I will not which I will not explain fully, but well, it is written in our paper with Julia Woods and Tom Clays, and also in a subsequent paper by Charlier, Clays, and Ruzza, which appeared recently in 2021. And these asymptotics of this unbounded solution of KdV are quite interesting also for applications, because can be used, and we use them to give asymptotics of the tails of the narrow wedge solution in the theory of Kaldar-Parisi-Zhang equation. Okay, so this is something that we obtained in 2020, 2021, and more recently with Giulio Luzza, we used the same approach to study a discrete version of this finite temperature IV kernel. And we just say a few words because this is still a work in progress. But the point is that there is a discrete version of the finite temperature IV kernel, which is the finite temperature discrete Bessel process, Bessel kernel. So this kernel, which is expressed here in this form, is given not as an integral, but as a sum on some points L, which are located for convenience here on the semi integers. So on the points 1/2, 3/2, 5/2, and so on. And instead of using IV function, here you're using Bessel function of the first kind, okay? And the sum, you're taking the sum over the index of this Bessel function, okay? And of course, also here, A and B are half integers. So this discrete Bessel kernel is a kernel associated to an operator acting on small L2. And the interest from the point of view of applications is that these kernels define a certain point process, which is associated to a certain deformation of the Poissonized Plancherel measure on the space of Young diagrams. Okay, and a little bit mimicking or reproducing what we did in the case of the deformed IV kernel, we can associate also to the study of the determinant of this operator, so this function that I define as FU LS, a discrete Riemann-Hilbert problem, discrete in the sense of Borodin, which treated the case in which this sigma is equal to the indicator function of the positive semi-integers. And so it was just natural to ask what are the analog of the equation that we obtain in the continuous case in this discrete setting. And not surprisingly, but actually it was not an easy task. What we can prove is that, well, now this kernel that we have here, it depends on two variables, L and S. L is the argument of the Bessel function that you are using, and S is the position of this indicator function that you are using here. And what we discovered is that this function FU LS actually a tau function for a certain reduction of two-dimensional total. More precisely, in formula, you can prove that this function FU LS satisfies this equation, which relates on one side log derivative of FU with respect to L with discrete log derivative of the same function with respect to the variable S, because here the variable S is a discrete variable. S lives in the semi-integer. So this is a reduction of two-dimensional total equation. And actually, we also managed to find sort of initial condition for this solution, in the sense that the log FU of LS behaves in this way with respect to the variable L squared. Okay. So the conclusion, or the temporary conclusion, is that this approach that we use for the finite temperature IV kernel is actually quite robust, because you can use it for integrable kernel as the ones that I'm speaking about, and Thomas Botten also spoke about them, and also for discrete point processes like this. Okay, this was simply a small preview about some work in progress that I'm doing with Giulio. And yes, another interesting thing is that well, the reason why this discrete Bessel process has been studied by Dan Béthéat and Jérémy Bouthier is that in a certain limit that now I will describe, this function FULS, it converges to the distribution that we were studying before, these Q, which were deformation of the Tracy-Widom distribution. Okay, so what we did was to take the same rescaling that Béthéat and Bouthier used, which is the following. We define epsilon as 1 minus u, the u appearing here in this function, and you send that to 0, and you send L to infinity in this fashion, and S also to infinity in this fashion, fixing these variables t, and x. Okay, and then you define a certain function f xt, before it was L and S. Well, just plugging this this scaling inside, and if you expand formally your two-dimensional total equation in epsilon, you find that the first order are identically satisfied, and then at the order epsilon power 4, you find this sort of bilinear equation, and this is actually equivalent to the KdV equation for the log derivative, for the double log derivative of f plus x over 2t, which is telling us precisely that this reduction of two-dimensional total that we found in this setting is precisely the discrete version of the KdV equation that we have in the continuous case. Okay, so this is the result that we are working on in this moment. Okay, and now I will speak about a different approach to the same kind of kernels that we had, which is something that we developed with Thomas Botten and Sofia Taricone. And actually, this second approach, it applies to a more general class of kernels. So here I'm describing the kernels that we have now. Now we have n parametric families of kernels. Okay. Before small n is equal to 1, which are constructed as follows. We define some, let's call them phase function that we call psi n, depending on lambda and x, which are this function here. And we define higher order analog of IV function as this contour integral on some contours gamma plus and gamma minus that are written here. Okay, so these are higher order IV function. This satisfies higher order differential equations. And out of these IV function that are constructed in such a way that they decay exponentially at plus infinity, we construct some new kernels that we denoted in this complicated way, K, AI, N, S, and T. Okay, exactly as before. It's simply that before we were doing this integral using two IV function, and now we do an integral using this higher order IV function here. Sigma is the same as before, is the Fermi factor, and this T tilde is simply T exponential 1 over 2n plus 1. And we want to compute some freedom determinant that now we define in a slightly different way. We call them the NST. So now we have three parameters, well, three variables, this n, small n, s, which is a continuous variable here, and big T. And these are just the freedom determinant associated to these operators. Okay. I'm sorry that I had to change the notation. It's just because, well, in one way it's more convenient one notation, and in the other approaches, the other one is more convenient. But just to fix the idea, if you take D1 ST in this setting, this is the same thing as Q minus ST that we studied before. Okay, but now we have more general DN. Okay, so this is not just a generalization for the mathematical sake of generalization. It's actually the reason why we are interested in that is that this kind of freedom determinants appeared in the physical literature, okay, and especially in a paper by Painlevé, Majumdar, and Sher in 2019. And I will try to give my understanding of the physical meaning of this freedom determinant. So in this paper, Painlevé, Majumdar, and Sher, they studied a fermionic gas of n particle with this one particle Hamiltonian. And then they studied this gas according to the Boltzmann-Gibbs distribution, which is a distribution in which the joint law is given by this expression, in which we have here a sum of some determinants that are constructed out of a function of the one particle Hamilton. And then you have these determinants because we are studying fermions. Okay. And there is this result, which has been proved from a rigorous mathematical point of view by Dichen Wang in 2020 for small n equal to 1. But actually, in the physical literature, it is believed that this holds for arbitrary n, which says, in a way, that the law of the biggest particle in this fermionic system under a certain scaling is given by D1S. Okay, be careful. This is proven from a mathematical point of view for n equal to 1, but actually it is believed to be true for arbitrary n. This is due to this universality of this kind of distributions appearing in random matrix still. Okay, even if you change your initial model a little bit, the limiting laws, they don't change. You always have this D1 ST, which is nice from a certain point of view because it means that your distribution are really universal, they are important. But also a little bit disappointing because, well, we already studied this distribution. But actually, what is very interesting in this work by Majumdar, Shell, and collaborator is that if instead of studying the positions of this fermionic particle, you study the momenta, you arrive at different distribution. So in the moment representation, it is physically argued that the highest momenta of these systems scale in this way, which now depends explicitly on this small n. So you have this this sort of law of large numbers for the maximum of the momenta. The density behaves in this way, and here again we have a critical exponent which depends on small n, and it is physically argued that if you do this very explicit rescaling of the maximum momenta of your fermionic system, okay, the limiting law is given by this general freedom determinant that I was describing. So this DNST, with this n, which is now arbitrary, and means that instead of studying this freedom determinant associated to IV function, you have to study these higher order IV functions. Okay, so this is the physical motivation that led us to study these freedom determinants. Also, I should say that even from a pure mathematical point of view, you can prove that this operator satisfies some analytical conditions, and then using a theorem which is due to Mackey and Soshnikov, you can prove from an abstract point of view that this kernel defines some point processes. So also in this case, from a purely mathematical point of view, there are some point processes defined mathematically, and we are studying the position of the largest particles and these point processes. I will give right away the theorem, even if now probably it will sound a little bit obscure, and then I will give a little bit an idea of the proof and some more details. But anyway, the main result that we obtain is a Tracy-Widom formula for these freedom determinants. The Tracy-Widom formula says that is identical formally at the one that we had before. It says that these freedom determinant dn st are given by a double exponential of this type, exactly the same formula as before, but something has to change. And what changes here is that this u, it changes with n, and instead of solving the integro-differential Painlevé equation, actually it solves the nth member of the integro-differential Painlevé hierarchy with some boundary condition. Okay, so what is this integro-differential Painlevé hierarchy? Well, actually, it's something that for n equal to 1, of course, reduces to the equation by Amir, Kovin, and Castel. The second member of this equation has been found by Kajebrink in 2020. And, well, it's known in general that, here I'm stating something that is very well known here, I believe. The Painlevé equation is a self-similar reduction of the modified KdV equation. Then you have classically the Painlevé hierarchy defined as a set of equations which are obtained as a self-similar reduction of the equation of the modified KdV hierarchy. And what we have here is an integro-differential generalization of this stuff. Okay, I will say something more before afterward if I have time. So how do we deal with this kernel? Well, these kernels can be written exactly as the IV kernel in several different ways. And the expression that we like in our case is these triple integrals in which we integrate on this contour gamma plus, gamma minus, and r. And you integrate this exponential of this function psi that I defined before. Let me just go there. This function psi here, okay? And using a sort of Fourier transform that is due to the fact that you have here this function psi, we prove that this freedom determinant dn st can be written as freedom determinant of certain operator on the contour gamma plus and gamma minus, which are integrable of IIKS type, but of infinite dimension. Okay. Actually, this approach that we are using in the case t going to infinity, so in the case in which we don't have operator value irremaneuverable problems, is something that we developed in 2012 with Marco Bertora and then also with Tom Claes and Monica Girotti. And how much time do I have?
I think something like 15 minutes. 15
minutes, okay, I have plenty of time. So I can describe a little bit this operator that we have here, the operator that we have here is written in this way. So you see this as the shape of an integrable kernel of infinite dimensional because you have an integral against R, okay? And R here, this R is associated to the variable Z that we integrate against sigma prime, okay? And then we have this vector K, K1, the vector K1, K2, and M1 and M2, okay? Which are vector that depends on lambda. Lambda will be the variable in the Riemann-Hilbert problem, and Z. Z lives in this space HP, which is just the p copies of L2 of R weighted with this Fermi factor d sigma. Okay. And then we will denote with IHP the space of Hilbert-Schmidt integral operator on HP with kernel on this space, which means simply that we are studying, well, for instance, for p equal to 2 by 2 matrices in which the entries are operators that are operators on this L2 R d sigma. Okay. And associated to this function K and M, we have a certain family of rank 1 integrable operators with this kernel here. Okay. So in this setting here, lambda will be a parameter on our contour, the contour of the Riemann-Hilbert problem, but then these are themselves operators with respect to the variables x and y. Okay, operator on this space R2R. Okay, and the operator valued Riemann-Hilbert problem that we have is the following: we are looking for a certain function x, which is matrix valued, and the entries are themselves operators. Okay, and this x is analytic in lambda. Lambda is on the all complex plane except to this contour gamma plus and gamma minus, and we have jump condition on gamma plus and gamma minus, which are given by this operator nmk. Okay, and everything here looks very complicated because we have operator valued stuff. But if you just look carefully of what we have, this is just an operator valued generalization of the Flaschka-Newell Riemann-Hilbert problem that you have associated to Hastings-MacLeod solution of Painlevé. Okay, and accordingly, having the Riemann-Hilbert problem, you can study an associated Lax pair, and the precise result is the following. So before we design this multiplication operator M1 and M2, you construct a vector with them, and you take the solution of your Riemann-Hilbert problem multiplied by M. And you have that this operator valued vector N of lambda satisfies a Lax pair, in which here you see a lot of bold-face letters, because these A and B, these are matrices that are polynomial in lambda, but then the coefficients AK, A hat, do N, B0, and B1, these are operators. These are operators that are written, well, some of them are written explicitly here, okay? Here, instead of writing the operators, we just wrote the kernels, so U, X, Y, V, X, Y, and so on and so forth. And if you are lost in this moment, but you remember the Riemann-Hilbert problem associated to the Painlevé equation, well, these U, X, Y, and V, X, Y, these are kernels now of some operators, but this U at the end is the analog of the solution in the classical setting of the Painlevé equation. Okay, and indeed this is how it appears in the setting of Flaschka and Newell. Okay, and then you study the compatibility condition of these two equations that we have here. Okay, and actually what you study is this function that depends on S and x, okay? And this is just the diagonal of the operator. So it's uxx here, okay? Here we are in a Hilbert space. So I define this, this product here in this way. We have this L2 weighted with this Fermi factor, okay? And for n equal to 1, we recover this equation that was the equation that I was showing you before, and this is the integro-differential Painlevé 2 equation. But then you have more general equation that are written here. This is for n equal to 2, this is for n equal to 3, okay? Now, this function u, it depends on s. S here is the time of the hierarchy, okay? So when here I write u second, it means second derivative with respect to s. And then x is the variable that stays in the Hilbert space, okay? So when we write u wedge, it means that we are integrating against x, okay? And you have these equations. If you just pretend that these u are just scalars, these equations that you have here reduce to the Painlevé 2 hierarchy, the classical one, okay? But this is more general. And here I have a complicated slide that I don't want to speak about. The only thing that you have to retain from here is that when you have the Painlevé 2 hierarchy, the classical one, you can pass from one member to the hierarchy to the other one using the linear recursion. And here also we have a recursion, a recursive way to go from one equation to the other. And it is somehow complicated, but it's simply an algorithm. And you can go from one equation from the other very easily, okay? And actually, this recursion that we found is a recursion that in the classical case, so in the case in which the temperature goes to infinity, was something introduced by Hélène Ayrault in 1979. So it's something very classical that survives in this operator valued setting. Okay. This is more or less the last slide that I have. As I said before, in the classical setting, the Painlevé 2 hierarchy arises as a self-similar reduction of the modified KdV hierarchy. So do we have an integro-differential modified KdV hierarchy here? The answer is yes, we have, okay? We have to introduce two variables, t1 and t2n plus 1 for every small n in this way. And once you have your solution V to the integro-differential Painlevé 2 hierarchy, you define U by this formula, vice versa. You have U, the solution of Painlevé 2, and you define V in this way. And then you have that this V is a solution of the integro-differential modified KdV hierarchy, in which, let me just say something about the notation. Here, T1 is the space of the hierarchy, okay, T1. T2n plus 1 is the 2n plus 1 time of the hierarchy. And this x variable that we have here is just this, the additional variable that you add because you are in a Hilbert space, okay? Is the one that you integrate against sigma, okay? And we have a general integro-differential modified KdV hierarchy, which can be written explicitly with some recursion operator. And of course, if, for instance, you look at the first member, you have something like this, okay? You have an equation like this. These two members, please have a look at these ones. In the scalar case, they just sum, okay? And they give you 6v squared vt1, okay? But here in this integro-differential stuff, they are split in two, okay? But this, of course, is an integro-differential version of modified KdV. So the conclusion is that, sorry. The conclusion is that when we study these integro-differential Painlevé equations, you have two different approaches. Either you study them with classical Riemann-Hilbert problems, meaning finite dimensional, or you study them with operator-valued Riemann-Hilbert problems. And one might say, well, it's easier to study them using finite dimensional Riemann-Hilbert problem, and this is true. Because, for instance, in this way, you can study asymptotics using nonlinear steepest descent, Dave's zoo nonlinear steepest descent. But in a way, studying these operator-valued Riemann-Hilbert problems, you find more structures, because you realize that beside of this theory, you have some integro-differential version of classical integrable hierarchy that maybe are worth to be studied and appears in some other applications. This, I don't know. But even from a pure mathematical point of view, I think that they are very interesting. Okay, and this is the conclusion. Thank you very much for your attention.
Thank you for the nice talk. Are there any questions? So, may I ask you some probably stupid questions about this integral-differential Painlevé equations? So, is there any explicit relation between them and ordinary Painlevé equations with the same numbers, or it's just a kind of similarity that we replace some u squared by integral of u squared? We don't hear you.
So the question is that if it's just a similarity or there is a general setting in which you can put both of them?
Yes. So in a sense, is it just a name, or there can be some relation between one Painlevé and
no, actually, what is nice is that, okay, sorry. So here, since for the sake of the presentation, from the very beginning, here I said that sigma is this one, okay? But actually, in the first approach, so in the one that we used with Giulio and Tom Kleis, actually, you can take sigma more general, okay? And for instance, you can take as sigma the indicator function of 0, infinity, okay? And in this case, what you obtain is exactly the Painlevé 2 equation, the classical one. So in a way, when you study how to, yes, when you study the Riemann-Hilbert problem associated to this vector f and h, if you take sigma, which is a general sigma, you get this integro-differential Painlevé 2 equation. But then, as a special case, if this sigma is the indicator function of 0 to plus infinity, you get Painlevé 2. The point is that you get Painlevé 2, but this Riemann-Hilbert problem is not the classical one we are used to. It's not the one with the Stokes data on the 6 rays. Okay, is another Riemann-Hilbert problem that is just on the real line, on 0 to infinity. But this is something classical that was already known, because there is this article by Kapayev in which back in the 90s, he was trying to reduce the Tracy-Widom result using integrable kernels, and it ended up with these Riemann-Hilbert problems, which gives Painlevé 2. So in a way, this setting here, this 2x2 setting, gives at the same time the classical theory and this general one. And one more thing, you also see this from this picture here, in the sense that you have this psi here. Now this psi here in general, since you have a jumps which is 1 minus sigma z, This will not give you any isomorphic stuff because the jump still depends on Z. But if sigma is piecewise constant, you end up with some isomorphic stuff. And indeed, if sigma is just a Heaviside function, you get Painlevé 2. If you have many different discontinuities, you get a vector valued version of Painlevé 2. And this has been studied by Tom Kleis and Antoine Doran. So in a way, this 2x2 setting really gives the two theory together.
Okay, thank you.
Thank you.
So, and I probably want to ask another question. So when people say a hierarchy of some equations like KP, then it means that there are several commuting flows in the sense that different equations in the hierarchy know about each other. So is it true that when say a Painlevé hierarchy, then it is just a set of equations which do not interact with each other or not?
They don't commute themselves. I mean, when you have modified KdV hierarchy, this is what it means. It's a hierarchy in the sense that the flows, they commute one to the other. But when you get this self-similar reduction, the equation, of course, they don't commute anymore one with the other. What was it the question?
So the question was, is it just a word hierarchy, which means that actually just the set of equations, or there is something different?
Yeah, when I totally understand your point. When you arrive to the Painlevé 2 hierarchy, well, since this stuff they don't commute, it's just kind of a word. The point is that when you see the Riemann-Hilbert problem that you study, for instance, in this case, one reasonable way to call it a hierarchy is that the singularity structure that you have is the same as just at infinity, the order of the singularity goes with n. So in a way, this is one reason why you call it a hierarchy, because you have the same singularity structure, but the order of the singularity grows with n, in a way. But it's true that you say hierarchy in the case of PDEs, and then everyone knows what you mean because these are commuting flows. In the case of the Painlevé, hierarchy is a little bit an abuse of language because it's not a hierarchy in the sense that there are no commuting flows.
Thanks. Probably I will ask the last question. So how to formulate the problem for this integral differential Painlevé equations in a sense. So, for example, for just second order differential equations, we know that a generic solution depends on two initial parameters. And what is the situation with this integral differential equations, and what is which part of their solutions is covered by your Proton determinants?
You mean how you fix the solution? This is the idea, right?
Yes, if you just start from the equation.
You mean, yeah, you start from the equation and you are interested in the space of solution. This is what you mean?
Yes.
I think that, okay, this is I didn't say that, but I think that from a mathematical point of view, this is really what it would be interesting to do. And my hope is that in a way, what one should do is to define some operator, and in this case, I think that the operator value setting is better. My hope is that eventually you can prove that there is an operator valued version of the isomorphic surface associated to Painlevé 2, which gives the space of solution, in the sense that we have one particular solution, we have some Stokes data, which are given by these operators. My hope is that in a way you can construct a theory in which you have Stokes data, which will be non-commutative anymore because these will be operator, that gives you something like the usual surface that you have, for instance, for Painlevé 2, the cubic surface, but with some operator valued variables. So a sort of quantization of the classical theory. But this is wide open, I believe. But I think that from a mathematical point of view, this is what really would be cool to study this kind of stuff.
See. Thank you.
Thank you, Pasha.
Are there any other questions? Okay, so if not, let's thank Mathieu again.
Thank you. Thank you very much.
And we have